Welcome back. Today we are breaking down power series solution of second order linear differential equations step by step using Leibniz-Maclaurin's method. We will walk through exactly how to set up your infinite series, find the recurrence relation, and build your final solution. Let's get started. So I've highlighted the steps for the Leibniz-Maclaurin's method. Step 1 is to apply Leibniz theorem, just like we have learned in the previous lesson. We differentiate every term in the given differential equation nth times using Leibniz formula. Then we build the recurrence relation, that is, we set s to 0 in our newly differentiated equation and we arrange it to isolate the highest order derivative. This becomes your recurrence relation. Next is to calculate the coefficients by plugging in values of n. N could range from 0 upward or 1, 2, 3 upward. So we'll plug in the values of n into your recurrence relation to find the numerical values of the higher derivatives at s equal to 0. This will eventually be expressed in terms of your initial conditions, which are y of 0 and y1 of 0. Now we build the series by substituting those evaluated derivatives directly into the standard Maclaurin series expansion formula. We will review the formula in the subsequent slide. And finally, we simplify and solve by grouping the like terms together. That is, we factorize the y of 0 factor and the y1 of 0. We simplify the fractions and plug in any specific boundary conditions if the problem provided them. For our first example, it says determine a series solution of the equation d square y over dx square plus s multiplied by dy ds plus y equals 0. And we can recall that the square y over dx square can be written as y subscript 2, while dy over dx can be written as y subscript 1. So the equation can now be rewritten as y subscript 2 plus s multiplied by y subscript 1 plus y equals 0. Then we apply the Leibniz formula. We start with the first term, which is y subscript 2. Now we need to identify our v and our u. And remember that v is the one whose derivative eventually becomes 0 after a number of successive differentiation, while u is the one whose n differential coefficient can be easily obtained. So for y subscript 2, our v is equal to 1, the invisible coefficient 1. So if we find the first derivative, v1 equals to 0 because v is what? A constant. Now for our u will be equals to the y subscript 2. Now if we find the n derivative of u, we just add n to the value in the subscript, so we have y subscript n plus 2. And now using the Leibniz formula, we'll be making use of the first term in the formula only, which is u subscript n multiplied by v. And when we multiply both, when we substitute the value for u subscript n and we substitute the value for v, we got y subscript n plus 2. Now for the second term, s multiplied by y subscript 1. So for this second term, our v will be equal to s, the algebraic factor. So when we find the first derivative of it, we get 1. And derivative of s in respect to s is equal to 1. And if we find the second derivative, it will equal 0, which eventually cancels out in the series. Now for our u is y subscript 1. So u subscript n will be equal to what? Y subscript n plus 1. And we now have to get u subscript n minus 1 because our v actually stops at v subscript 1. So we also need to get u subscript n minus 1 in the formula. So now when we substitute n minus 1 to u, the value of u, which is y subscript 1, that is like writing y subscript 1 plus n minus 1, which now equals to what? Y subscript n. So when we bring that together in the formula, we'll be using the first and the second term of the series formula now, which is what? U subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1. So when you substitute the values for this, we will eventually get s multiplied by y subscript n plus 1 plus n multiplied by y subscript n. And for the third term in the equation, which is y, so our v is also equal to 1 and our v subscript 1 is equal to 0. Now our u is y and our u subscript n is just purely y subscript n. When we substitute the value into the formula u subscript n multiplied by v, we just get y subscript n. Now we combine all the differentiated terms by writing out the nth derivative of the first, second and third term in the equation. So we have y subscript n plus 2 plus s multiplied by y subscript n plus 1 plus n multiplied by y subscript n plus y subscript n equals 0. So we'll notice that y subscript n appears twice, which means we can factorize. When I factorize y subscript n, so we have a factor of n plus 1. Then we try to get the recurrence relation by substituting s equal to 0 into the differentiated term equation, and you notice that it is the second term that has s, which means it cancels out. Now we have y subscript n plus 2. You notice that I write it in a square bracket with a subscript of 0. So this is just to say that these are the values of y when s equals 0. So now plus this third factor, which is n plus 1 multiplied by y subscript n of 0, which is equal to 0. Now we'll make the higher derivative, the higher order derivative, the Soreto formula. So we have y subscript n plus 2 of 0 equals, when I carry this one to the left hand side, it is now negative n plus 1 multiplied by y subscript n of 0. This is now our recurrence relation. So next is to calculate the coefficients. And okay, most exam or textbook questions will give you a boundary. They will usually phrase it like find the series solution up to the s raised power 4 term, or find the first 4 non-zero terms of this power series. So once you hit that specific requirement, you stop calculating the value for n. But if the question doesn't specify where to stop, just aim for the first 3 to 5 non-zero terms, or until you can clearly see the pattern to write a general rule. To calculate the coefficients, we plug in values of n into the recurrence relation. To find the numerical values of the higher derivatives at s equals 0, such as y subscript 2 of 0, y subscript 3 of 0, and so on, which will eventually be expressed in terms of the initial conditions y of 0 and y subscript 1 of 0. Now for my recurrence relation, I have y subscript n of 0 on my left hand side. I can easily start my values of n from 0 so as I can get this initial condition y of 0. So now my n is starts from 0 to 3, and you can add more. So when n equals to 0, we plug in 0 into the recurrence relation. I have y subscript 0 plus 2 of 0 equals minus open bracket 0 plus 1 multiplied by y subscript 0 of 0, right? Now 0 plus 2 here equals 2, so that means y subscript 2 of 0 equals to minus y of 0, because y subscript 0 is the same thing as writing y. Now when n equals to 1, I have just add 1 to this one, that is 1 plus 2. So now I have y subscript 3 of 0 equals to minus 2 multiplied by y subscript 1 of 0. When n is equal to 2, we have y subscript 4 of 0 equals minus 3 multiplied by y subscript 2 of 0. You can see the pattern. But since y subscript 2 of 0 can be written in the initial condition, which is minus y of 0, we substitute that in place of y subscript 2 of 0. Now our y subscript 4 of 0 equals minus 3 multiplied by minus y of 0, which equals to what? Plus 3 multiplied by y of 0. Now when n is equal to 3, y subscript 5 will be equal to y subscript 5 of 0 equals to what? Minus 4 multiplied by y subscript 3 of 0. Also, y subscript 3 of 0 can be written as minus 2 multiplied by y subscript 1 of 0. When I substitute that into this equation, I have 2 times 4 multiplied by y subscript 1 of 0. I left it as 2 times 4, not 8, because there is a pattern to review. Now we can review the Maclaurin series formula. For y is equal to f of s, our y is given as y of 0 plus y s multiplied by y subscript 1 of 0 plus s is power 2 divided by 2 factorial multiplied by y subscript 2 of 0, and it keeps adding up in the series with this pattern: s is power n divided by n factorial multiplied by y subscript n of 0, where y subscript n of 0 denotes d raised power n of y divided by d s raised power n at s equals 0. And in some textbook, y subscript n of 0, the way I wrote it in square brackets, can also be written like this. Now we substitute the evaluated derivatives into the Maclaurin series expansion formula. So I wrote out the formula again. Now we substitute the values of our higher derivatives. Y is equal to y of 0. Y of 0 is an initial condition. Y1 of 0 is also an initial condition. Now from the higher derivative, we have s is power 2 divided by 2 factorial is equal to 2 times 1. Now y subscript 2 of 0, we got minus 1 multiplied by y of 0 plus s is power 3 divided by 3 factorial is what? 3 times 2 times 1. Then our y subscript 3 of 0, we got minus 2 multiplied by y subscript 1 of 0. Now for the s is power 4 over 4 factorial, we have 4 times 3 times 2 times 1 multiplied by, so for y subscript 4 of 0, we got 3 multiplied by y subscript of 0. Now for y subscript 5 of 0, we add this 2 times 4 multiplied by y subscript 1 of 0, and we have s is power 5 over 5 factorial as the factor. Now it keeps adding up. Now when we simplify, the first term remains the same, second term remains the same, but for the third term, minus 1 times plus s is power 2 is now minus s is power 2. Then 2 times 1 is equal to 2. The next term, minus also times plus, here we have minus at the numerator, s is power 3. Now for the denominator, 2 cancels out, we have 3 left, that is 3 times 1 is just 3. The next term we have s is power 4 over, okay, for the next term 3 cancels out here, so we have 4 times 2 times 1 left, so I just wrote it as 4 times 2. Then the factor here is what? Y subscript of 0 plus the next term is s is power 5 over 5 factorial. Now for this one, 2 and 4 cancels out in the denominator, so we are left with 5 times 3, then y subscript 1 of 0, and it keeps adding up, right? Now when we factorize out the initial condition, which is y of 0 and y1 of 0. So when we factorize y of 0, we'll be left with 1 for this first term here, 1. Then anyone that has y of 0 will be written in this bracket here, so that is minus s is power 2 over 2 plus, we also have this s is power 4 over 4 times 2 plus, so we have to like denote that the formula keeps expanding. Now plus our second initial condition is y1 of 0, so now when we factorize this out, we are left with s as a factor here. Then we also have this s is power 3 over 3 minus s is power 3 over 3 plus, then the last one here is what? S is power 5 over 5 times 3. Then it also keeps adding up, and that is our final answer for the example 1. For our example 2, it says find the power series solution of the equation s multiplied by d square y over dx square plus dy dx plus sy equals 1, given that at s equal to 0, y is equal to 2, and dy dx equals 1. So for this example, we have a boundary condition. So the first thing to do is what? To rewrite the equation in this format, which is s multiplied by y subscript 2 plus y subscript 1 plus sy equals 1. Now we apply the Leibniz formula, and I wrote out the formula again, which is y subscript, the n derivative of y is equal to u subscript n multiplied by v plus n multiplied by u subscript n minus 1 multiplied by v subscript 1 plus n multiplied by n minus 1 over 2 factorial multiplied by u subscript n minus 2 multiplied by v subscript 2, and it keeps adding up. Now when we find the n derivative of the first term using the formula, we got s multiplied by y subscript n plus 2 plus n multiplied by y subscript n plus 1. You know how to do that already. Now for the second term, y subscript 1, the n derivative is equal to y subscript n plus 1. For the third term, the n derivative is s multiplied by y subscript n plus n multiplied by y subscript n minus 1. And for our right hand side, we have 1. So if we find the n derivative of 1, it's just equal to 0. Now we combine all the differentiated terms, we add them together, you see, equals to 0. Now we factorize. For our equation, we have y subscript n plus 1 appears twice, so we have a factor of n plus 1, and okay, that's all. Now this is the factorized equation. Now we substitute s equals to 0 to get our recurrence relation. So any factor that has s, we eventually cancels out. This first term we cancels out, the third term also cancels out, so we will be left with n plus 1 multiplied by y subscript n plus 1 of 0. Remember why we write it as of 0. Now plus n multiplied by y subscript n minus 1 of 0 equals to 0. Now we express the higher derivative as Pareto formula. So y subscript n plus 1 is higher, obviously. So we move the n multiplied by y subscript n minus 1 of 0 to the left hand side, and to make y subscript n plus 1 stand alone, we divide both sides by n plus 1. So I have minus n over n plus 1 multiplied by y subscript n minus 1 of 0. This is our recurrence relation. So the next thing is what? To substitute the values of n. So we also have to look at the left hand side to get the initial condition y of 0. What value should we substitute? So if I substitute 0 here, I'll have 0 minus 1, which is y of minus 1, y squared minus 1, which is not necessary. So but if I substitute 1 minus 1 is what? 0. So that means our n values must start from 1, so it can go on to whatever length you want. Now when n is equal to 1, we have y subscript n plus 1 of 0, right? So that is y subscript 1 plus 1, which is now y subscript 2 of 0, equals, so we have minus n over n plus 1, so that is what? Minus 1 over 1 plus 1, which is 2, open bracket, y subscript n minus 1, n minus 1, 1 minus 1 is what? Is 0. So we just have y of 0 here for our first term. Now for n is equal to 2, we have y subscript 2 plus 1 of 0 equals to minus 2 over 3 multiplied by y subscript 2 minus 1 of 0. That gives us y subscript 3 of 0 equals to what? Minus 2 over 3 multiplied by y subscript 1 of 0. For the next term, when n is equal to 3, we have y subscript 4 of 0 equals minus 3 over 4 multiplied by y subscript 2 of 0. And remember that y subscript 2 of 0 is expressed in the initial condition, so we'll substitute that. So I have minus 3 over 4 multiplied by minus 1 over 2 multiplied by y subscript of 0. So you can leave it like that without simplifying. Then, okay, I can cancel out the negative sign. I have just positive 3 over 4 multiplied by 1 over 2 multiplied by y subscript of 0. Now when n is equal to 4, y subscript 5 of 0 will be equal to what? Minus 4 over 5 multiplied by y subscript 3 of 0. Now we substitute the values of y subscript 3 of 0, which is equal to this. Then when we simplify a little by just cancelling the negative sign, we have positive 4 over 5 multiplied by 2 over 3 multiplied by y subscript 1 of 0. Also for n is equals to 5, we have y subscript 6 of 0 equals to minus 5 multiplied by y subscript 4 of 0. And when we substitute the values of y subscript 4 of 0, we get minus 5 over 6 multiplied by 3 over 4 multiplied by 1 over 2 multiplied by y of 0. Now we substitute the evaluated derivatives into the Maclaurin series expansion formula. So I wrote out the formula again, expanding it up to s power 6 over 6 factorial multiplied by y subscript 6 of 0. Now we plug in the values of our higher derivatives. For this first term and the second term are initial conditions, so there's nothing to change here. Now for y subscript 2 of 0, we substitute the value, which is minus 1 over 2 multiplied by y over y of 0, and 2 factorial is equal to 2 times 1. And for this one, we have s power 3 over 3 factorial is written as 3 times 2 times 1 multiplied by the values of y subscript 3 of 0. We do the same thing for s power 4. We just substitute all the values we got for these higher derivatives. Then the final one is what? S power 6 over 6 factorial is now 6 multiplied by 5 times 4 times 3 times 2 times 1 multiplied by, then y subscript 6 of 0 is equal to what? Minus 5 over 6 multiplied by 3 over 4 multiplied by 1 over 2 of y of 0. Now we'll simplify. The first term remains the same, second term remains the same. For the third term, let's see. Okay, minus 1 multiply plus s power 2 at the numerator, so we have minus s power 2. Now for the denominator, we'll notice there's a pattern. We have 2 times 1 and we also have 2, so which is the same thing as writing 2 power 2. That is square of 2, right? Then we have y of 0. Then for the next term, we have, okay, negative multiplied by positive at the numerator, we have negative s power 3. Then the denominator, 2 cancels out 2, so we are left with 3 multiplied by 3, which is also 3 raised power 2 multiplied by y subscript 1 of 0, plus this one, 3 cancels out in the denominator, so we have 4 and 2 repeated twice, so which is the same thing as writing s power 4 over 4 square multiplied by 2 square multiplied by y subscript of 0, plus for s power 5, 4 and 2 cancels out in the denominator, we are left with 5 multiplied by 3 and 5 multiplied by 3 twice. So that's how I write it out like this. And for the last term, s power 6, it has a denominator of 6 power 2 multiplied by 4 power 2 multiplied by 2 power 2 multiplied by y of 0. Now we factorize out the initial condition y of 0 and y1 of 0. So for y of 0, we have factors like this first term now gives us 1. Then the third term also has a factor of y of 0, so we have minus s power 2 over 2 raised power 2. This fourth term also has a factor of y of 0, so I add it here, which is plus s power 4 over 4 square multiplied by 2 square and the last term here also has a factor of y of 0, so which is plus s power 6 over 6 power 2 multiplied by 4 power 2 multiplied by 2 power 2, and it keeps adding up in the series. Now for the second initial condition, so that is plus y1 of 0, y subscript 1 of 0. I also write out all the factors, which is s, we have minus s power 3 over 3 square. We also have plus s power 5 over 5 power 2 multiplied by 3 power 2, and also it also keeps adding up in the series. Now the question gave us an initial condition boundary, right? So which is at s equal to 0, y is equal to 2. So if y is equal to 2 at s equal to 0, it will be written as this, that is y of 0 equals to 2. And they also said dy ds is equal to 1. dy ds can be written as y of y subscript 1. So at s equal to 0, it is written as what? Y subscript 1 of 0 is equal to 1. Now I just replace this outer factor y of 0 as what? 2, and this y1 of 0 as 1. And you know, 1 multiplied by anything is that thing, so I don't need to write out the 1 anymore. And that will be the end of our power series solution of second order linear differential equation. So stay tuned for the next part, and make sure to engage and subscribe on the channel.